Hello everyone, my name is Mark. Welcome to my Calc 3 videos. And today we're going to talk about Lagrange multiplier. So the first question I have for you is, what and where can Lagrange multiplier help find about a function? Since we're still talking about extremer problem, I think the first question comes pretty naturally, right? We're still going to find what we're going to find is the function extrema, right? Function extrema. But where, right? Where of the function extrema, right? It has to. This Lagrange multiplier can only help us help us find the extrema on the boundary of the function. Okay, so let's say I have a function of x and y, and my boundary equation is g. Right? What is the condition for maximum and minimum to occur, right? So I think the professor during your lecture has already taught you that maximum and minimum will occur at when the gradient of the function is parallel to the gradient of the constraint function. Okay, and this is this Lagrange multiplier. Right now I'm just trying to teach you how to solve these problems, but the concept of Lagrange multiplier will have a lot of potential in many field of studies, especially in optimization, in the field of optimization. So let's say you're trying to maximize your strength, minimize your material use, things like that. That's called an optimization problem, and the Lagrange multiplier plays a big part of that. So I digress. By the way, this is my lecture notes. You will be able to find them in my resources folder. So let's return to my slides. So the key condition is that the gradient of f is going to be parallel to the gradient of g. Before I showed you the second set of questions, I want you to I would like to show you that this pretty useful video, understanding the Lagrange multiplier visually. Okay, so this is a pretty cool video that I would like to show you, and then I'm just gonna I would encourage you to take your time and actually watch it. But right here,
x and y, subject.
Right here, right, the maximum or minimum of a function is subject to a constraint must occur when the gradient of f is parallel to the gradient of g, right? This is how you can represent the concept of Lagrange multiplier visually, okay? But I would highly encourage you to watch the whole thing. Again, it's a really cool video to watch, and it could help you understanding. But I'm not gonna show it to you here. I'm not gonna play a whole video here. We're gonna move on. So, how does the method of Lagrange multiplier differ to the first derivative test? Okay. So the idea of the difference between Lagrange multiplier and the first derivative test, which we have talked about from the previous video, which is the finding the absolute extrema of a function, right? So there is a difference, right? I think it's pretty obvious. The Lagrange multiplier is using the concept of gradients, right? Gradient based. I mean, it's gradient. I'll just call it gradient. And then first derivative test is kind of gradient, but it's more about plug and then plug and check at critical points or at important locations of the points, right? At points. So which type of constraint should you use Lagrange multiplier or first derivative test? So let's say I have a constraint that's a rectangular constraint or triangular constraint. Which one would you use? Right? So this is if I were you, I would definitely use first derivative test. Okay, but let's say I have a circular constraint. Would you still use first derivative test? Well, technically you can, right? But when the constraint is circular or elliptical, this provides me an opportunity to use, or spherical in the case for 3 variables. So elliptical, circular, spherical constraints. This provides me an opportunity to apply Lagrange multiplier. So which one can help you find extrema inside the constraint, right? So we have talked about, just from the previous slide right here, right? We have talked about Lagrange multiplier can only help you find extrema on the boundary. It has no capability for you to find extrema inside the constraint. So when the question asks you to find the extrema inside the constraint, don't hope that Lagrange multiplier can help you get the answer that you want. You gotta use first derivative test for a constraint extrema problem, right? If it's unconstrained, it's gonna be second derivative test. So this answer to this question is gonna be just FDT, right? First derivative test. So before I jump into the problems, I want to create a quick sort of a mind map, or like a tree diagram at page, to show you what we have learned about so far, right? So we have extrema. Overall, we have been talking about extrema problems recently, right? So but for extrema problem, we have 2 different types, right? We have 2 different types. We call them local extrema, or local extrema, and then absolute extrema. Right. So, or we can call them relative, or global, right? So that's 2 different types of constraints. And then for local extrema, right, the only way to solve this type of problem is going to be second derivative test, SDT, second derivative test. But for absolute extrema, we have 2 different approaches to solve this type of problem. One way, we have first derivative test, right? That's what we use for things that's like constraint that has rectangular shape or triangular shape. But let's say if we have a spherical, elliptical, or circular constraint, that provides me an opportunity to use Lagrange multiplier. So there you go. This is kind of the sort of the analysis diagram that you should apply for every extrema problem, so that you know what you're looking at, and then you can apply the correct solving steps to solve this type of questions. Okay? So today we're going to take a look at this problem. It's from exam 1 spring 2019. And then let me go back let's go ahead and set up the problem. So you have the 1-pager, you have the 1-pager solution. So let's go ahead and stack them up. Oh, actually, never mind. This is not the question that we're looking at. I don't think so. Okay, give me 1 second. Okay, solved. Copy, and then we'll paste right here. Sorry for the hiccup, but we should get going right away. So the extreme values of this function with constraints of x squared plus y squared plus z squared equals to 4, right? So this is spherical constraint. So so this is I think everybody can agree that this is an extrema problem by reading the words extreme values. But how do you know that this is local extrema or absolute extrema, right? So the 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 question is asking us the extrema of the function with constraints, right? So the question has locked us into the region of interest on the sphere. So we are trying to find extrema on the sphere, right? And the sphere is falls into the category of spherical constraint. So this is telling us this is probably a Lagrange multiplier problem. So we have circular constraints or elliptical constraints, or I'll add another word, or spherical as well. Right? And it's asking us to find extrema on the constraint. So the first step is what I want you to do is to identify the function as well as the constraint themselves. So that should be easy step to do, just to help you prepare for it. So f equals to 3x plus 2y plus 6z, and then g equals to x squared plus y squared plus z squared minus 4 equals to 0. So that's step 1. And step 2 is that we're going to find the gradients of the function as well as constraint. So step 2, we're going to have the gradient of the function equals to 3, 2, 6, easy enough. And the gradients of g would equal to 2x, 2y, and then 2z. Right, so that's pretty straightforward, pretty standard. And then what we're going to do is we're going to utilize the idea of setting up the gradient of f is equal to the Lagrange multiplier times the gradient of g, right? Since the gradients of the function and the constraints are parallel to each other, we can set up a constant, so they are scalar multiple of each other, right? So that's the fundamental idea behind them, right? Scalar multiple of each other. That's why the Lagrange multiplier exists. So so let's go ahead and set it up. I'm gonna so we're going to have fx and fy and an fz, right? And then equals to the lambda times g of gx, gli, gz. So this is part that we just set up over here. But what you would realize is that since this is a 3-variable function, and then we also have a Lagrange multiplier, that's 4 variables, but we only have 3 equations, right? So that's unsolvable, or have multiple infinite solutions. So we don't like that. We want to pinpoint down our answers of the extrema locations. So we're going to need to have one more equations to make this system of equations have unique answers. So the first constraint that we're going to utilize is the constraint functions themselves, right? That's why I want you to identify the equation of the constraint early on, so that you can always come back to it. So in this case, we're going to apply this third step as 3 equals to lambda times 2x, and then 2 equals to lambda times 2y, 6 equals to lambda times 2z, and then the constraint itself, I'm just gonna go ahead and copy and paste to here. Okay, that's easy enough. So now you have 4 equations, 4 unknowns. So before I jump into step 4, I'm gonna go ahead and play around with this equation a little bit. Okay, so let's say x equals to so if I play around with this equation, first equation, we're gonna have 3 over 2 lambda, y would equals to lambda, z equals to 3 lambda. So if we substitute x, y, z into the last equation, so we're going to have 3 over 2 lambda squared plus lambda squared plus 3 lambda squared equals to minus 4 equals to 0, right? So we have 4 equations, 4 unknowns. So step number 4 is that we're going to solve for x, y, z and avoid solving for lambda if possible. So in this case, we are unable to solve. It's going to be difficult to avoid solving for lambda. So we're just going to ahead and solve it for lambda straight away, and then plug in back to the x, y, z. But keep in mind, lambda is just some sort of a constant that help us to get to the answer that we want, which is x, y, z. The exact value of lambda, we don't really care about that. So whenever you get a chance to use some sort of basic algebra skills in system of equations to cancel your lambda out, do that, right? Because we don't really care about the values of lambda. We only care about the values of x, y, z. But we're unable to do that in this case. But as you practice your past exams, whenever you see that's the case, do it. So step 4 is we're going to have, so if I have this equation expanded out and then solve for it, we're going to have lambda equals to 4 over 7. So that means our x is going to, actually this will be plus and minus 4, 7, but 4 over 7. So but in the positive case, we're going to have x, y, z equals to 6 over 7, 4 over 7, and then 12 over 7. Okay? And then in the case of lambda equals to negative 4 over 7, these values are just going to be reversed. Pretty straightforward. So minus, minus, minus. And then finally, we're just gonna go ahead and plug in these coordinates into the function, the function expression themselves to find the extremas. So step 4 actually. Step 4. Hold on a second. Actually, never mind. It's just some numbering problems. Not really a big deal. Okay, step number 3. Come on. Okay. Here we have step 0, right? It's a preparation step. Step 4. So function of this value is going to equal to 14 if you plug them in back into here, and then a function of the other value, I hope you can understand it because this is a linear equation. Well, the function itself is linear. This is just going to be negative 14. So there you go. So you have the maxima and then you have the minima. Boom. So this is how you can find the extrema on the constraint using Lagrange multiplier. So the process again is straightforward, but you just need to know what type of question you're looking at, right? I hope you start, as you watch my videos, I hope you start to see the importance of identifying the type of problem you're looking at and apply the correct solving techniques. So in case of Lagrange multiplier, right, the constraint needs to be circular, elliptical, or spherical, and then the question is asking you to find the extrema on the constraint, and then you can just utilize the idea of the gradient of f is parallel to the gradient of g with a Lagrange multiplier, all right, and then we also need the constraint itself to form a system of equations that's solvable, and then we're going to go ahead and solve for the x, y, z. We'll plug into the function, and then we can get the extrema on the constraint. So that's it for me today. I hope you learned something. I hope you enjoyed the video. Thank you very much for watching, and I will see you in the next one.